Generally, there is no force in central orbit other than the central force. But if in the medium in which central force act there be a resistance, then this central orbit is said to be central orbit in resisting medium. Okay, that is, there be another force other than the central force, which is resistance force, and here we let the resistance force varies as the square of the velocity. Now if we take the resistance force is R, then this is equal to K V square. Okay, and let P or F, say F be the central force. Right. Now we draw a rough sketch of the central force or central orbit. Let this is the pole and this is the initial line, and this be the central orbit, and let the particle be at P at any time t. Okay, and tangent at P is P t, cut the initial line at t, and this angle is known as phi. This angle phi is a standard notation of differential calculus, which is the angle between tangent and the radius vector. Okay, and this is r, this is theta. So the point is r theta, right? And this direction is the radial direction or positive direction of radius vector, and this is the cross radial direction. This is the perpendicular to the radius vector. Now here the resistance force act along this direction. This is R, because a particle if move to, let this be initial position of the curve, let this be A, and at the point P where AP arc length, this is equal to S, right? This is the initial position of the curve, and resistance vector or resistance force R, this is equal to K V square per unit mass, and here the central force act in this direction. This is minus F, because this is F, and this is in the direction of center of force, right? Now in this direction we know that Fr, this is the radial acceleration, and radial acceleration is known as minus F, right? Minus F, because F act along O, so in the opposite direction Fr, this is equal to minus F, and F theta, this is cross radial, this is equal to 0, because F is the central force. Now since this angle is theta, so this is also theta, this is also phi. This angle and this angle are opposite angle, and this is pi by 2 minus phi, right? So the component of r vector, this is minus r, because r is act along the downward direction or opposite to the motion of the particle, so this is minus r, and the component of r along f theta is equal to minus r, this is sin phi, because this angle is pi by 2 minus phi, so the component is r cos pi by 2 minus phi, and this is obviously minus, so minus r sin phi, and the resultant acceleration along cross radial, this is equal to 0 minus this, so this is minus r sin phi, and the component of minus r along the radial is given by, this is minus r cos phi, okay, because this angle is phi and the component of minus r is equal to minus f minus r cos phi. So we know that in central orbit the radial and cross-radial equation of motion are the first equation, radial equation. Radial is r double dot minus r theta dot square, and this is equal to fr, which is given by minus f minus r cos phi, right? And what is r? R is equal to k v square. So we get this is minus f minus k v square cos phi, and this is known as 1. And the cross radial equation of motion is 1 by r d dt of r square theta dot. This is equal to cross radial acceleration means minus r sin phi. Actually this is fr and this is f theta. This is radial acceleration and this is cross radial acceleration, and this is given by minus r means k v square into sin phi, and this is 2. Now these are two equations of motion of the central orbit in resisting medium, where resistance are this is varies with the square of the velocity. Now we know that from the differential calculus, sin phi this is equal to r d theta by ds, and cos phi this is equal to dr by ds. Okay, we put these two values in 1 and 2. Now we first put the value of sin phi in the second equation. We get this is 1 by r d dt of r square theta dot. This is equal to minus k into v. V means ds dt, and this is ds dt whole square into this is sin phi, that is r d theta ds. This is equal to minus k into ds dt into r d theta by dt, because 1 ds and 1 ds are cancelled out, right? So as ddt of r square theta dot by here 1r and here is also 1r, so r square, and this is theta dot, so we get theta dot here, and the right side is minus k into ds dt. Okay, and this gives d of r square theta dot by r square theta dot. This is equal to minus k ds, and integrating we get log of r square theta dot. This is equal to minus ks plus an integrating constant which is c. To find the integrating constant c, we let here initial moment of momentum about center of force O is h0. Okay, and we know that moment of momentum h, this is equal to r square theta dot. In central orbit, this is a standard result. Okay, so we put first r square theta dot, this is equal to h, and we put the initial condition, that is we get at t equal to 0 initial s, this is equal to 0 because at initial position the particle is at a where s equal to 0, and we measure the s from a, and r square theta dot this is equal to h0 because this is generally r square theta dot is h, and we let here this is initial h0. Okay, so we get the condition as log h0, this is equal to c, and we put the value of c here, we get log r square theta dot by 80, this is equal to minus ks, and this gives r square theta dot, this is equal to h0 into e to the power minus ks. And this relation can be written as theta dot, this is equal to h0 by r square into e to the power minus ks, and we name this relation as 3. Now in central orbit r, this is equal to 1 by u, r dot, this is equal to minus 1 by u square into du dt, and we get r dot, this is equal to minus 1 by u square du d theta into d theta dt, and d theta dt means theta dot, and we put the value of theta dot from 3, and we get the relation as minus 1 by u square into du d theta into h0 by r square into e to the power minus ks. This 1 by r, this is equal to u, so we cancel out 1 by r square and 1 by u square and get the relation, that is r dot is given by r dot, this is equal to, sorry, this r dot, this is equal to minus h0 du d theta into e to the power minus ks, and this is named as 3. Okay, this is the third relation, sorry, this is not third, this is named as 4. This is the fourth relation. Now we differentiate again the fourth relation and we get r double dot as r double dot, this is equal to, if we differentiate du d theta with respect to t, then we get minus h0 into d2u by d theta 2 into d theta dt, and here remains e to the power minus ks, and the second term is, this term is constant, the derivative of second term, and this is plus h0 du d theta into k e to the power minus ks and ds by dt. Right, now we put the value of d theta dt, that is theta dot, this is equal to this relation, and ds dt, this is equal to v, and get r double dot, this is equal to, we write first this term because this is positive, this is h0, this is k v e to the power minus ks into du d theta, and the second term is minus h0 into e to the power minus ks, and d theta dt means h0 into u square, h0 into u square into e to the power minus ks again, so this is e to the power minus 2ks. Okay, that is h0 and also d2u by d theta. This relation is r double dot, and we name this relation as relation 5. Now we put r double dot and theta dot in equation number 1, that is the radial equation of motion. We get here r double dot means, we first this relation h0 k v into e to the power minus ks into du d theta minus, this is h0 h0, that is h0 square into u square into e to the power minus 2ks into d2u by d theta. This is the first term, r double dot, minus r, r means 1 by u into theta dot square, so this square, so we get H0 square by r to the power 4, and this is into e to the power minus 2 ks. This is given by equal to minus f minus r means k v square into cos phi. Cos phi means dr by ds. Now we put 1 by r to the power 4. This means into e to the power 4. Here we take common e to the power minus 2 ks from these two relations. This and this we get, and the first term it becomes h0 kv into e to the power minus ks into du d theta minus here h is h0 square and here also h0 square, so we take common h0 square into d2u by d theta 2 plus this is uq into e to the power minus 2 ks. This is equal to minus f minus k into, we write v square as v into ds dt. One v remain fixed and one v we write ds dt, and into here dr ds. So we get the right hand side as minus f minus kv into this is dr dt, so r dot, and we put the value of r dot from here and get minus f minus, this is minus and minus, plus kv h0 into e to the power minus ks into du d theta. Okay, we get this relation from 1. Now we see that this term, this is h0 kv e to the power minus ks du d theta, and also this term is on the right hand side kv h0 e to the power minus ks du d theta, and these two terms are cancelled out. Okay, so there remains minus f and there remains this term. We cancel out minus from both sides and we get h0 square into u square. We take common here. This is u plus d2u by d theta 2 into e to the power minus 2 ks. This is equal to f because minus cancel out, and this gives u plus d2u by d theta 2. This is equal to capital F by h0 square u square. Looks like the original central orbit, but there remains one term. This is equal to e to the power 2 ks, because in the left hand side it is minus, so in the right hand side this is plus, and we get finally this is the differential equation of central orbit in resisting medium.